Hello everybody, my name is Jean-Baptiste Charraud. I am working at the CA and preparing a PhD supervised by Grégory Jeunesse and Marc Torrent. My work is focused on the search on new materials for the energy, and for this purpose I am working on numerical simulation at the atomic scale, and more precisely on algorithms able to predict crystal configurations. My talk will then be specifically focused on a type of this algorithm called the ab initio random structure searching method, or shortly random searching. First of all, I will present you the global challenges related with new materials prediction and using numerical simulation at the atomic scale. It will be followed by a description of the general principles related with random searching. Afterward, I will speak about the implementation of this algorithm using ab init, and at the end, I will conclude by some considered improvement using machine learning potential. So, in a lot of domains, progress is very dependent on the search of new materials, able, for instance, to store in a more dense way the energy and transport it more efficiently. As a result, one have also one increase of the conditions a material has to fulfill, and it becomes complicated for the experimentalist to identify the most promising materials without the help of the numerical simulation at the atomic scale. This numerical simulation can help them to identify what are the best candidates and to help for precise characterization of these materials. As a result, one have the development of new algorithms using supercomputers, artificial intelligence, and also software able to make precise prediction on the physical features like ab init. And this is typically in this context that is inscribed the development of the random searching approach. I want now to speak about the general principles of this algorithm. The output of a random searching structure algorithm is one crystal configuration. In other words, how the atoms are combined together inside the material. To describe it, one needs to have degree of freedom. Some degree of freedom are directly related with the description of a primitive cell geometry. Another part is related with the position of the atom inside it. When we have one crystal configuration, one can compute one energy using DFT computations, and as a result, we can describe the energy as a function of this degree of freedom. With this definition, the energy can be considered as a surface called the potential energy surface. This is a multidimensional surface, and as a result, it is not so as easy as I represented here. The main purpose of the crystal structure prediction algorithm is to explore the surface to retrieve the global minimum. This global minimum is worth because it corresponds to the crystal configuration being the most stable and to the materials which can appear in the experiments. But this exploration can be quite challenging because the more one have atom inside a primitive cell, the more increases the dimensionality and then the number of the local minimum to explore. And the search and the surge is even exponential. So, the exploration of this surface can be organized in several cycles, and each cycle can be divided in several steps. The first steps consist by making a sample of the potential energy surface. It follows some rules and heuristics coming from, for instance, experimental data. It can be represented here. We generate crystal configurations following this rule and heuristics, and each configuration can be represented by this blue circle here. After making this generation, we perform a local exploration of the potential energy surface by moving each blue circles to the local minimum of the surface. It corresponds to optimize the crystal configurations to minimize the energy. It can be held by DFT optimization, for instance, with ab init functionalities. At the end, one obtains optimized configuration, and a part of them having the lowest energies, and it corresponds to structure candidates. At this point, two ways can be considered. The first one consists by taking into account the feature of the selected configurations for the next cycles. In this case, it is called a genetic approach. On the contrary, one have a random searching approach, and this is typically the strategy chosen here. So I want not to speak about the implementation of this method using ab init. The main point enabling the efficiency of this method is a parallelization over images. One image corresponds to a crystal configuration, which is initially generated and optimized afterward. In this parallelization, one can have a processor or group of processors taking each one image, generating a first configuration and making the optimization task. With this strategy, we can thus explore simultaneously several regions of the potential energy surface and then speed up the search. The global management of this parallelization can be represented like that. First of all, for each images, one generate initial configurations. These initial configurations are then optimized using DFT computation, for instance, and then get implemented algorithms in ab init. After making this optimization, one obtain structures, and we compare the physical properties between each others. The structures having the lowest energies are structure candidates, and on the contrary, those having the highest energies can also be taken into account for further cycles. It can be plugged, the configuration having the highest energy can fill a database, and this database will influence the next cycle. When a configuration will be generated, it will be compared with those which have been rejected. And if it appears that this generated configuration is too close from one which has been rejected, it will be taken over by another one. The idea behind this comparison is to avoid to generate and optimize one configuration which have been yet explored and rejected beforehand. So I want not to specifically speak about the generation process of these configurations. First of all, the user has to enter some informations like a reference volume for the primitive cell, and also the number of chemical formula considered. In other words, the number of atom and type of atom. From these informations, one generates a first geometry for the primitive cell. This generation has to respect a value for the volume. And this volume's value is determined following a probability distribution centered at the reference volume entered by the user beforehand. At this point, one has to generate the atomic positions. It can follow some optional biases. One can impose, for instance, chemical environments when a specific type of atom has to be surrounded only by another type. We can also use the fixation of a sublattice, and another possibility is to employ symmetry operation to generate the atomic positions. At this point, one have atomic configurations, and we need to check whether or not the atom pairs are enough separated between each others. One can imagine several strategies. One can apply several strategies. The first one consists by checking each atom pairs to verify if distance conditions are fulfilled. If two atoms are too close between each others, the atomic configurations will be taken over by another one. Another possibility is to use repulsive potential to move enough the atom apart from each other. After making this verification, the atomic configuration is then taken into account for structural optimization. So I want now to introduce some application of this algorithm. At the CEA, we are interested in superhydrides, which are materials made of metallic atoms and hydrogen, and which offer very interesting opportunities for the hydrogen storage in high density and also for superconductivity, and then for the energy transport without any loss. A first study was to validate the algorithm on this kind of materials, and we were able to retrieve some published reference structures of yttrium superhydrides. You can see here the published reference structures, and below what we were able to obtain after running the random searching algorithm. And you can see the complete identification between these two kind of configurations. It proves that the algorithm is working, and we are thus able to make predictions to discover new materials. And it was held. We made some new predictions for manganese superhydrides and hydrides. Here you can see the configurations we were able to predict. And what is interesting is we are predicting materials able to form under pressure, but which have very important stability, and which thus can offer very interesting opportunities for the hydrogen storage in a high dense way. So I want to end this talk by some considered improvement of the current algorithm using machine learning potential. The starting point of this improvement is the following. Among all of the steps required to hold random searching approach, 99% of the computational cost is due to DFT computation. As a result, it can be quite challenging to predict new structures if we have several decades of if you have several decades of atoms inside the primitive cell. The idea is then to take over the DFT computations by fast structural optimization using machine learning methods. So global workflow can look like that. First of all, as before, one generates a huge number of configurations. We can generate a very huge number because they will be fast optimized by the machine learning potential. After making this fast optimization, one selects the configuration on the basis on filter on the appearance frequency of the configuration and of the predicted energy. This selected configuration are then subject to second point DFT computation to know the precise physical properties. And these properties are then plugged into the training database employed to update the model. At this step, one updates the machine learning model with the new training database. We make some comparisons between the predicted physical features and those which are computed directly by DFT, mainly on energy, forces, and stress. And after making this update, one generates further cycles. At the end of the last cycles, one selects configurations and one runs full DFT optimizations to retrieve the most stable compounds. This approach was applied on the tin crystal structures. After just making one iteration of the workflow, we were able to retrieve the reference structures of tin. This axis here corresponds to the appearance frequency, and the vertical axis corresponds to the predicted energy. By making a filter on the appearance frequency and on the predicted energy, we were able to select few configurations in which are included in red the reference structures. These selected configurations are then subject to full DFT optimization, and at the end we were able to find the expected crystal structures. And moreover, the model used was able to make very precise prediction on the energy, forces, and also stress. It proved that this approach is working, and moreover, we were able to spare a huge amount of time computations because we generated 10,000 structures, and we were able to optimize it in 1 CPU hours. If you will do the same work with full DFT optimization, it will require around 1 billion CPU hours. So, as a conclusion, there are two ways today to use random searching with Abinit. First consists is based on one internal implementation, which will be available soon in the version 8.12. And one other possibility is to use also external scripts. For now, we are considering some improvements. The first one is based on machine learning potential, which are enabling the search of more complex compounds having more atoms inside the primitive cell. And probably, we are probably considering for this further implementation the use of ABPI functionalities too. So I thank you for your attention, and if you have questions, don't hesitate.